Hello, this is Alan Folmsby speaking from Hawaii. I hope you're having a pleasant vortex out where you are. The magnetic vortex is quite a small one, though. Iron has 12 lines in a vortex, and that gathers lines about a meter away. You've seen magnets affecting things a centimeter away, a meter away. Much bigger than the nucleus of iron, but really that's where it comes from. So I made an iron mock-up to show you the vortex around the North Pole. North Pole is when the ring of protons has a current going in it that's clockwise. And a South Pole would be when the two rings of protons are both going counterclockwise. And I'm going to point that out to you in a couple of minutes here. For example, see, I could just show you what the static nucleus theory has proposed for iron, cobalt, nickel, and copper. So right over here from on the right, iron has a ring there in green of protons. There's 12 of them. Gadolinium would have 18 protons in the ring. And I'm going to show you that in a couple of minutes. But you can see copper on the left has a ring, but it's been ruined by the extra couple of protons. Makes a short circuit between the axis and the ring. So I'm going to show you another mock-up where 57 styrofoam spheres are shown you for the common iron isotope, iron 57. And iron 56 is even more common. And then on each of the protons, I'm going to show a stick, which represents a line of flux coming from each proton in the ring. And these sticks go out to the electrons. And the eddy current of electrons is made up of the little sticks here. And then Lenz's law will be shown using geometric reasoning. So I'm going to get to that real soon. And what technically I'll be saying, in addition to the mock-ups, is talking about the vortex fan-out and growth, that magnetic fields grow. As you might have noticed, as on the sun or in magnets, they're not just limited to 1 millimeter away. As you move an iron magnet into a piece of metal, there'll be a growth of these field lines going throughout. Now, a small nucleus drives a wider eddy current remotely in copper. So the small iron nucleus is driving a fan-out from the tiny nucleus to a much wider eddy current remotely in a copper electromagnet, for example. Now, I've proposed Magnetime, which is the dimension number 5, and that grows in flux to gather lines of flux in the vortex. And gathering is an important thing as the flux lines rotate. But let's go over to the camera and look at this mock-up now. All right, here's the styrofoam mock-up. And on the bottom I've got iron, and then far away there's some other element or something that's going to get caught up in the vortex. So on the bottom we see this is like an iron nucleus, much like this one here. This one has the green protons forming a ring. And the larger styrofoam one has white protons on it here. So the thing is that the top ring is guiding any flux from the bottom ring. So there's torque inside this iron nucleus here. This is a scale of about 30 trillion x magnification of the iron nucleus. And there's a manganese nucleus up on top, and you see that the flux from these wooden sticks is connecting to the wooden sticks, the flux lines of the manganese, and that rotation can occur as you bring them together. And if you move them apart, then the vortex cannot reach out far enough to gather the manganese flux. But if you bring some motion, the iron comes in motion here, then you could capture some of the molecules that are nearby, say within 1 nanometer or something. And these kinds of ideas are mechanistic, but they're quite practical for spintronics, which I'll be talking about later. There is a recent book on spintronics that I'm going to be featuring in just a second. And let me bring around the camera to look at that book. Almost ready. All right, I'm ready to talk about this book by two authors, and it's called Spintronics for Next Generation Innovative Devices, edited by Katsuaki Sato and Eiji Saito. So it's copyrighted, so I can't really show you what's inside of it, but I believe on a couple of pages here we have some wisdom about nanoscale magnets, about thin film nanoscale magnetic devices. So this is nanotechnology, but that doesn't mean it's tiny little nanometer cubes. No, it's a big thin film. It's a nanometer thick. And that's about 5 atoms thick. So these little atoms I'm going to be showing you with these wooden stick bonds, this is actually an accurate way of portraying magnetic phenomena. Now, you may also be familiar with the everyday magnetic phenomena of magnetizing a piece of iron with a magnet, like this. All right, so that is now magnetized. Notice that you don't just do it one sweep. You have to go across the iron many times to magnetize it, over and over. And what you're doing is you're combing, like this. Just like a comb goes through hair, so does the iron flux vortex go through all the lines of flux of the target. And you have to comb it over and over again so that you get all these things to align to the new north and south pole positions. Now, iron can also be demagnetized, and that needs a reversal back and forth, so that the direction is important for that. So I'm going to now get ready to read from this book by Mr. Saito and Saito. All right, now some of the things, like I was saying, is Magnetime is one of the dimension 5, and it grows to great lengths from magnetization, and it follows also the non-crossing law is important for all of this. As that mock-up showed you, these wooden sticks of flux cannot cross other lines. So this is what makes induction, as these flat flux membranes induce motion in other membranes. There's either a spin meshing or a spin clashing sometimes for repulsion, for example, and that would be exclusion. And then sometimes there's ohmic cycles where these lines of flux do cross, and it causes some heating. Now in the B field, in the nuclear magnetic resonance, this is actually like a combing of lines of flux, and that even a steady B field is really a motion of Weber. Of a Weber is the number of lines passing through an area per second. So that if you have a steady B field, there's really action going on, and there's motion sweeping and combing across your nuclear magnetic resonance target molecules. Combing your target molecules in NMR. And all these electrons and lines going around really means there's a proton current. Since there's a pairing between each proton electron, and the electrons are going around, then the proton current also is moving along with the electron currents. And it's a superconducting current of protons in iron. And then torque is also given, like as I was saying about this static nucleus theory. In this picture I'm showing that one of the 12 in a loop is paired with one electron on the right there. And the 3 dimensions are 2 of the space-like dimensions, EX and EY. And then there's another one going the opposite direction, Magnetime. And the growth formula is that Magnetime is equal to HX plus HY. In other words, you add together the motion in the X direction of the proton current, and that adds to the length of Magnetime. That's how magnets reach out across a vacuum, a meter away, to capture lines of flux in a copper electromagnet, a meter away from an iron magnet. It's because that one dimension, Magnetime, is growing with HX, and rotation drives this HX. That is the motion as that rotation of the proton ring current, so this one dimension reaches out across space. And that HX is moving in a circle. In the previous slide it was EX and EY, so I changed my names. And it grows to the remote copper coil. And the purpose of this speech is that saying that iron has outreach of Magnetime to gather lines of flux in a piece of metal far away across a vacuum. And bonds in molecules will slip by this type of outreach. They'll get rotated and temporarily moved slightly but bonded molecules do not get captured as, say, electromagnet would, where there is a ring available in electromagnets. And this all is leading up to itinerant proton currents that must exist in copper. I'm just going to skip ahead a couple of slides here. And, oh, here's it. Spintronics, page 163 through 167 by Sato and Saito. And I'm going to be reading something out of here of these two subjects in spintronics. The spin polarized current is what they call it in the book. And I'm calling it the eddy current and the co-eddy current in my idea. Now, in this book, they also talk about self-induced spin currents, and they are dissipationless, almost like a superconductor. Now, under my nomenclature, I'm saying it's the proton itinerant current, similar to in platinum. And you probably have noticed that the shapes of the rings in iron are not perfect round circles, but they are let's see. I'm going to pause a second here as I'm pushing buttons. All right, so undulators. Yes, so I'm going to move along here back to the camera and page 163. Okay, 163. Pure spin current. Figure 9.1 shows what the pure spin current is. That's a magnetic thing. We'll say in this experiment they have like a piece of cobalt sitting on a piece of platinum. And the little spins come out of the cobalt and they move down through the platinum some distance of 1 micron or something. So a spin polarized current is a type of charge current, but the numbers of up and down spin currents are not the same. Only one kind of spins flows in one direction in a perfectly polarized current. A pure spin current is a completely different current from the ones mentioned above. The same number of up and down spins flow in opposite directions, so there is no charge flow. Moreover, a pure spin current ideally possesses a time reversal symmetry, resulting in a dissipationless current. So, right there, that's the punchline, the dissipationless current. That this book, Standard Science, is saying that there's a dissipationless current that you can measure the spin a micron away from where it came from, a nanometer type thing, application. So I'm going to go to page 167 now. All right, so this is about the self-induced effect, like the undulator. This is what I'm trying to tie together my undulator shape in the iron nucleus, or the gadolinium nucleus, with standard science. I'm trying to tie it all together. Sukahara et al. Reported that ferromagnets can generate self-induced electromotive forces under the ferromagnetic resonance due to its spin-orbit interaction. This self-induced effect induces the modulation of the ferromagnetic resonance, which is quite similar to signals when dynamically spinning injection is succeeded. So, to paraphrase what he's saying, is that there's a self-induced electromotive force, and that this is present unavoidably, and it could be misinterpreted in other experiments. So, putting this all together, I'll just go back to the slide and finish up this section here. All right, I'm back at the control panel. And I just showed you the Spintronics book and the kind of things that they're talking about there. And that was about the spin polarized current all going one way. So let me give you more of an explanation of why this is going on like this. In the iron rings that I was showing you, the shape undulates. And therefore, the electron eddy current undulates. That makes energy available to be measured. It doesn't have to be measured, and the energy doesn't have to be dissipated anywhere. But it's available under this dissipationless eddy current. Now, in standard science, they always talk about unpaired electrons in iron. Like if you go to the internet and you search, like, why is iron magnetic? And they'll say, oh, well, the electrons are unpaired for the iron crystals and molecules and atoms and things. And they don't really tell you about the nucleus. And see, the electrons are unpaired because the nucleus and the rings are polarized. The ring currents are both going the same way. Therefore, the electrons are polarized, and they're all spinning the same way. And polarization of spin means that all of the 12 charges are spinning the same direction. That's why there's unpaired electrons in iron. Now, demagnetization is, of course, done all the time. It's very useful. And let's compare that with anti-ferromagnetism, which is other materials, not iron, for example, but other materials like chromium or something. And iron can be demagnetized, and chromium is usually demagnetized, although locally you could have magnetization. And all these things depend on solid-state nuclear orientation being static. That in a bar magnet, the iron nuclei are not rotating around wildly or anything. They have a static orientation compared to the bar. And this is standard science that says this in a book I have on NMR, nuclear magnetic resonance. And the demagnetization of iron, you have to, say, apply a north pole from the left side of the bar magnet, and then you apply a north pole from the right side of the bar magnet, and you keep reversing it hundreds of times until it's demagnetized, as opposed to anti-ferromagnetic elements where you can demagnetize it from one side. Iron, you have to demagnetize it going from the left side and demagnetize from the right side and go on different directions. Anti-ferromagnetism, that's not true. you can demagnetize it from one side. Now, these itinerant proton currents are really useful in catalysts. For example, platinum and the itinerant proton currents are well known to be useful for, say, starting methane to burn at room temperature when passing over a thin wire of platinum, like in exhaust pipes where thin wires of platinum cause exhaust to burst into flame again, because the hook has a shape of almost a ring. So a faraway molecule then can share in the proton current that is going to flow in this ring. And so current would flow out of the hook and into a faraway molecule, catalyze a reaction, and the current flows back to the other end of the hook. And this also justifies my belief that itinerant proton currents exist in electromagnets. Now, the magnetic vortex. In conclusion, I would just like to say that the mechanistic models that I've been showing are valid. Any quantum strangeness that teachers and high school teachers and professors, they're trying to tell you quantum things are not going to make common sense, and that you should not even attempt to use logic, geometric reasoning, inductive logic. Just follow the rules that the graybeards have set down, and that is quantum theory. No. Mechanistic models are valid. This is Alan Folmsby. I'll be back again next Wednesday, same time. Thank you. Bye.